Hello everyone, welcome to the introduction to the online lab sessions of Introduction to Electrical Engineering. So we have 5 batches this trimester, G1, G2, G3, G4 and G5. Each of these correspond to individual branches. The experiments for Introduction to EE would be of 2 categories. One would be experiments that we'll be doing on online circuit simulator, like the Fallstadt Circuit Simulator, CircuitVerse, Circuit Lab, or MHRD Virtual Labs. So the link for Fallstadt Circuit Simulator is right here. If you click on this, it will take you to another tab. I'll come to this in a little while. The second category of experiments are video-based demos. So certain types of experiments for which we do not have a very interactive simulator, we will do video-based demos. This is basically like introduction to certain components, familiarization with those components. Here you will have you'll be given a video assignment on Edpuzzle, and on that we will have a quiz and a augmented reality-based Viva. Okay, so example of AR-based Viva is also shown here in this video. You may click and go to it. So how the experiments would be held? The lab sessions would be held over Google Meet. And while we want most of the experiments to be performed individually, in first few experiments, you can have groups of 2. Okay? So this will be primarily based on your roll numbers. There are 5 sessions, so we'll have about 40, 45 or 50 students per batch. Every session would have one lab instructor, one staff member who will be assisting, and 4 TAs. TAs stands for teaching assistants. These are PG or PhD students who will assist in this course. So how would the reports be submitted? So in every lab session, there would first be a brief portion, say half an hour or so, where the lab instructor would explain what is to be done in that lab session. Right? You will be provided a manual. That manual will be uploaded on the Google Classroom. Now, I have created a separate Google Classroom particularly for lab experiments because all your lab reports have to be submitted online on Google Classroom. So there is a separate Google Classroom with all the lab instructors added as co-instructors. So in Google Meet, we will be able to create individual breakout rooms. And since we have 6 people in every lab session, including the lab instructor, and there would be about 24, 25, maximum 25 number of breakout groups of 2 students each. That means each member can actually look after 4 to 5 groups. Inside each breakout room, each group, like you have a group of 2 students, each group should keep screen sharing on, and there is an option that you would see inside the breakout room called request for help or ask for help. When you click on it, the meeting owner, that is the lab instructor, would get a message saying breakout room, say 24, is requesting for help. That means that's a cue for the lab instructor to click on that breakout room and go and answer your query. So this can be done by TAs also if TAs create their own meeting links, and 4-5 groups like that can be assigned, and the TA can also navigate between each of these breakout rooms. So why we're asking for screen sharing to be on? Because the whole thing has to be done on an online simulator. So for us to see whether you are really doing the experiment and for you to ask questions, it's important that you keep screen sharing on. Now, the platform that we are using, the online simulator, is not a collaborative platform. That means there is no login ID through which 2 of you can log in together and work simultaneously. Therefore, one student would be sharing screen and one student would actually be opening the Fallstadt simulator on their terminal, while the second member of the group can do a remote access to the first student's computer using a platform called like TeamViewer or any other remote access platform. Okay, this is just for the duration of the lab session, but allowing anyone to remotely access your PC has privacy issues, so please be very careful. So like after the end of the session, make sure that you have closed the TeamViewer session, you do not leave it open. The deadline of the report would be such that if you do a lab experiment today, The deadline for that experiment's report submission is next week, means next lab session, just the day before the next lab session. So if you have a lab session on Tuesday, that means the deadline for your submission is next Monday midnight. Each group needs to submit only one report. Both the students do not have to submit individual reports. Just one report per group, but make sure that you have the name of both the members in it. I will share a separate report template that you should follow. The report should basically contain these headings: objectives. What is the objective? Circuit diagram. Then for circuit diagram is what you make on paper, right? You use symbolic representations of different circuit elements and you make a circuit diagram. This is often also given in the manual. But if you were doing this experiment physically in lab here in IIT Jodhpur, you would be using a breadboard and you would be making physical connections, right? So for that purpose, I need you to make a schematic using a virtual breadboard using the platform called Fritzing. Okay, Fritzing or virtual breadboard, anything is fine. Now, Fritzing is a desktop application, but it does not work on Mac. It also does not have an Android option. So another very important thing that one should remember for these sessions is that you need to have a laptop for these lab sessions. It is important. You will not be able to complete these lab sessions over phone. And this was also announced and advised during your orientation. So please make suitable arrangements. So you will make a physical connection. I'll show you a demo. The link for downloading Fritzing can be found here. This is already a paid version that I have kept for this lab session. So please use this link. Otherwise, if you directly go to Fritzing website, it may ask you for some payment to download. So you may use this link directly. This document is already shared on the Google Classroom. Please refer to it. Other than this schematic, so you'll make this on a virtual breadboard or Fritzing. You will take a screenshot and you'll include it in your report. Then from the online simulator, you will also take screenshots of all the observed waveforms that are asked. You will have a section on observations and any calculations that you had to do, some inferences like what is the final conclusion. And along with every lab report, each group will also submit a short 60 to 90-second video explaining the observations and inferences. Because we are not meeting physically, so in order to familiarize us with you and who you are and how you do the experiment, and whether you really are understanding what's going on in the experiment, it will be really good if half the experiments are like recorded by one of your group mate and the rest of the experiments are by another, so that both of you have equal opportunity to make these videos. And this is a very short video, just like 1 to 1.5 minutes long. Not, please don't make longer videos. If you want, you can do a screen recording. There are some screen recording extensions available for Chrome which are free of cost. You can also use Screencastify, which is a free screen recorder for up to 5 minutes. That means since this video is just going to be hardly 1.5 minutes, right? So you can always use Screencastify. It can be linked to your Google account, your IITJ Google account, and that will be really convenient to you. So you can use screen recording and explain what you are doing on the screen with your waveforms, and this is what we did, and this is what we found. This is the reading that I've taken, and eventually this is the outcome of this experiment. Explaining this, every single group for every single experiment will submit a 60 to 90-second video. Okay. The link to download Fritzing is here. Please make sure that when you are submitting these reports that I'm talking about are typed reports. They are not handwritten reports. So you need to type the whole text. Wherever you have circuit diagrams, you are welcome to draw them on paper and take a screenshot or take a picture and upload. Okay, but overall, these reports are meant to be typed reports. Please do not plagiarize, because plagiarism means copying somebody else's report word to word, because there are softwares to check this kind of a copying, whether you've copied from the internet or you've copied from your classmate, we would find out, and if there is any kind of plagiarism, your report will directly be disqualified. There is no resubmission. Every couple of weeks, we will have a continuous evaluation of your lab experiments. So we may hold a short viva in each lab session, but that will be pre-announced, but you should still, keep yourself updated regarding the experiments. These are broadly how we've proposed the list of experiments. There may be somewhat little bit of change here and there, but more or less this we plan to cover all these experiments in this program. So the schedule is as follows. This document is already shared with you. So you have this second sheet which covers the entire lab schedule week wise. So week 1, week 2, week 3, and so on. This is your schedule. So you have 5 lab instructors, including myself. Mr. Gajraj Sharma, who's the lab superintendent, will also assist. He's a staff member, a technical staff member from the Department of Electrical Engineering who would assist in this course. More meeting links will be created in due time and you'll get to know. TAs also, we have a full list of TAs right now, but day-wise availability of TAs based on their class schedule is still to be finalized, and this we will update in the next couple of days. If you just go through this list, a batch-wise list, and in case you do not find your name here, please let us know immediately. In case you are not registered on Aryabhatta yet, please contact the Office of Academics immediately and fix this. So I'll now go to the software. So let me start with the Fritzing software. So when you click on this link, it will take you to so it should take you to a download link. Based on your system, download this. It will download a compressed file. Please extract that file. So when you extract the Fritzing folder and you open fritzing.exe, this kind of a window should open up. Click on breadboard and you would get one breadboard. Right now, in the lecture that I've shared earlier regarding familiarization with function generators, DSO, and breadboards, you already are familiar with how the connections on breadboard are made. Like these 5 holes, each of these 5 holes are connected to each other. That means you can have a node having 5 different branches. Each of these could be a node having 5 different branches. This entire row is connected to each other. This entire row is connected to each other. I would also need you to check out some components, some electrical components. So this is a breadboard. Now to make any connection on this breadboard, you need certain components. So on the right hand side, you see parts. There's a search button. Click here and you can type anything you want to include here. So let me type a resistor. Okay, so there are different resistors here, different families of resistors. Here on the bottom right side, you see an inspector. So this describes different components which are here on the left hand side, okay, on the editor. So I'm going to pick up one of these resistors, click and drag them here. Let me zoom in. I'm zooming in using the scroll button on my mouse. So this is a resistor. You notice that there are 3 bars of color and there is a 4th color. So if you're familiar with the color coding of resistors, please revise them because they would be very useful for you to identify what resistor this is just by looking at its schematic. So when you click on this, on the right hand side, this is being called R1 resistor, and it also shows where it is located here. So if you move this around, this will change, the location would change. This is from this family. It has a tolerance of plus minus 5%. The value of the resistance is 220. So here I could have changed the resistor value. At this point, I would also advise you to find out more about the standard values of resistance. So normally you cannot have every single value of resistance. It means it's not possible that there's a resistor of 50 ohms also, then there's a resistor of 60 ohms also. There are some standard values. Please read more about the standard values. Please read more about E6 series, E12, E24 series of resistors. I'll share some material with you on that. So here, when you click on the drop down button, you see a list of resistors. Okay, these are the standard values of resistors. Why are these values as they appear? Like, why is there 2.2 and then directly there's 3.3? Why there is 1 and then 10 and then you will find 100, 6.8? Why is it in this order? Please find out. Okay, they belong to a certain family of resistors, certain standard series of resistor. So from here you can select these values. So suppose I select, right now it's 220 ohms, so this is this color combination, right? But if I selected 1K, you notice how the color combination changes. Depending on the color code, the value of the resistor changes. So you can choose different values of resistors from here. I'll zoom out. I'm again zooming out using the scroll button on my mouse. So we're going to place this. Suppose I want to make an RC series circuit, right? So I need a resistor and a capacitor and connect them in series. So I'm just going to click and drag them here. So we notice that this row has become green, this row has become green. That means there is a connection between these two. And now anything you want to connect in series, if you want to connect anything to this resistor in series, suppose on the right hand side, you can connect to any of these 4 holes, right? So now I'm going to take a capacitor. I'm taking an electrolytic capacitor. Unlike a ceramic capacitor, electrolytic capacitor has a dielectric which is polarized. That means there is a certain polarity to this capacitor. And the positive side should be connected to the positive side of the battery. Okay. Unlike a ceramic capacitor which looks like this, it doesn't matter which is positive, which is negative, but the electrolytic capacitor is polarized. So I'm going to, this is also a type of ceramic capacitor. I'm going to remove this. So this is an electrolytic capacitor. I'm going to connect the plus side of the battery here and the minus sign of the battery here. You can also define these two bottom rails as positive and negative. Like you can just name them, keep them connected and keep them named like this. Say this is the top one is the positive rail and the bottom one is the negative rail. Just keep them like this, and any connections that you make on the breadboard, just make a connection to the respective rail. So you don't have to take this directly from here. So maybe I'll remove these. So you do not have a function generator here, but normally when you would be doing this in lab, you would take this to the function generator input. So let me define the top one as positive and let the bottom one be negative. That means if I connect a resistor between this and this, the electrolytic capacitor connected here, this terminal should be positive one, because that's the one which will be connected to the positive cycle. Okay, but here since it is negative, I need to flip this. So I was not able to change the values of that capacitor. So I've chosen a new capacitor. When you click on it, you see on the right hand side, the packaging, the voltage rating of this capacitor and the value of the capacitance. Note that every capacitor would have a voltage rating, that is the maximum voltage that it can handle. So we have to always make sure that whenever we are using any capacitor, it should have a voltage rating of more than what you would be using in that circuit, right? So this has a voltage rating of 6 volt, that means 6.3. That means I cannot attach a voltage source more than 6.3. I should not, otherwise it may damage this capacitor. We can change the value here. So for this particular family, what are the range of values? That also is shown here. Okay, so if I make the connection, I see that left hand side is negative while the right hand side is positive. So I need to flip this. Since it's an electrolytic capacitor, and I've decided that this top rail will be connected to positive and the bottom rail will be connected to negative. So to flip the terminal, I just select this and use this flip option, and it is going to flip its terminals. Now to complete the connection, so this part is connected. Now all I need to do is just take this and connect it to the negative rail. Okay, so now it shows me that the circuit is complete. It is also showing me all the nodes where I have made connections. Okay, so why I need you to do this is so that you familiarize yourself regarding how you would make these connections physically on a breadboard. Okay, so it's different from making a circuit diagram, because in circuit diagram you simply use circuit components, certain symbols that represent certain components, but you do not physically see how those components look like. But this kind of a platform would allow you to make those circuits physically. Remember that fritzing is just for making circuit diagrams. It is not a simulator, and all you need to do here is just make a circuit like this, skip the part where you connect it to the source, uh, and take a screenshot of this part, the editor part, and make sure you use the correct values of resistors which are given in your circuit. Please upload this in your file, right? So this is how fritzing would look like. So I'm looking at a circuit with a resistor value of 1K and a capacitor. I'm going to take something, I'll say 1 microfarad. Okay, so this is fine. 1K and 1 microfarad. This was physical diagram. Now let us go to the circuit simulator. So the circuit I'm trying to draw is a series RC circuit. So we've got a resistor of 1K and a capacitor of 1 microfarad. I'm going to connect this to an AC source or a pulsating, say a square wave. This is the part of the first experiment, and this is a circuit that I'm trying to make, right? So this is the source here. Let it have a square waveform having a maximum voltage 5 volt and minimum voltage minus 5 volt. So it has a peak to peak voltage of 10 volt. And this is the symbol. If it was an AC signal, I would have drawn it like this. Okay, so this is a circuit we are trying to draw. So coming to the simulator, if you Google Fallstadt circuit simulator, this is where you will land. You see a sample circuit and you see some options here. I would suggest you do everything on the full screen version so that the waveforms are more clearly visible to you. So click on the full screen version. Okay, and you see a sample waveform here. Let us start with some of the options that you see on the top. So you've got file. Okay, so file is going to give you options of opening a new file, importing certain files, saving, and all these things. So we'll come to this. Edit also has these regular edit kind of options like copy, paste, duplicate, select, zoom in and out. You also have this option of some keyboard shortcuts are shown here. Draw is the most important menu which we will be using. This is where you will find all the components. So adding a wire, adding a resistor, all of these also have keyboard shortcuts, like you simply press W and you can get a wire. Simply press R on your keyboard and resistor is selected. Passive components are those components which cannot supply power to a circuit. They can only store energy or dissipate energy, like resistors, capacitors, or inductors. They are known as passive components. So this is from where you select these passive components. Then every circuit will also have an input or a source, which in a physical lab, this would have been your function generator or a DC power supply. But in an online simulator, this is the tab from which you select different sources. So you've got option of inserting a ground, voltage source. So this is a DC voltage source, 2-terminal. That means it will have a plus and a minus sign also. So minus side, you will have to connect to the remaining part of the circuit. And you also have single terminal options of voltage sources, where the other terminal is by default uh, ground. Okay, so just to show you an example, say if I select a 2-terminal voltage source and I try to draw it, this is how it looks like, right? So it's a 2-terminal device. However, if I was choosing a 1-terminal voltage source, it looks like this. So it is understood that this part is connected to the plus side of 5-volt battery. Okay, and the other side is connected to ground. So this is understood. Uh, Typically, we will use, unless we are making an op-amp circuit where there are different various connections to the battery, we will usually use the 2-terminal source. Okay, you want to delete it, select, press delete on your keyboard. Then there are some other options like output label, adding LEDs, adding lamps, adding text box. If there is any point from where you want to record observation and you want to record a waveform, you can include a voltmeter node over there, like you're as if you're placing a voltmeter over there, and different others like ammeter. So these are all measurement related nodes, labels. Then there are some active components like diodes, Zener, transistors. We'll come to this later. Logic gates, some chips, flip-flop, sequential circuits. We'll use them a little later in the course. Okay. So we start with a blank circuit. So you go to circuits, select a blank option, and you've got a blank canvas, right? Now we want to draw that RC circuit. So we select draw, add resistor, click and drag, and you've got a resistor. By default, it's of value 1K, but if you wanted something else, you could just click on it and you could change the value here. Right? So K stands for kilo only. So just write 1K. It's okay. You could have also written 1,000. Apply. Okay. Next, I want a capacitor. So draw passive component. Let me add a capacitor. So we had chosen an electrolytic capacitor. So I'm going to choose an electrolytic capacitor like this. Okay. Again, by using the scroll button on my mouse, I can zoom in or out. Next, I want to connect a AC source here. So draw inputs and sources. I'm selecting a 2-terminal alternating voltage source. Something like this. Next, I want to connect a wire. So add wire. Make this connection. So my circuit is now complete. But remember that I wanted a square wave here. This is an AC wave source. So I'm just going to double click. And I see an option to edit this component. So maximum voltage is +5 is fine, but the waveform I want should not be AC. I want a square waveform. So from this drop down, I'll select square. I don't want any DC offset. That means I want the average value over a cycle to be 0. Frequency right now is 40 Hertz. Okay, let me make it 100 Hertz. I don't want any phase offset with respect to 0. I wanted a square wave, so I'm leaving this duty cycle as 50, but depending on the question, you may want to change the duty cycle. So I've selected a square waveform. I'm going to do apply and OK. So now my circuit requirement is complete. The capacitor that I had selected, I need a value of 1 microfarad, right? So I'm going to click on it. Right now it's 10 microfarad. I'm going to change it to 1. So to write micro, we normally use the symbol mu, right? But in this circuit simulator, you can simply use a U symbol to denote micro. So 1 U means 1 microfarad. Maximum reverse voltage is also to be mentioned for this electrolytic capacitor. So because I'm using a +5 to -5 kind of a voltage, that means at any given point, there could be about 10 volts of voltage. There's a maximum sweep is 10 volts. So I need that this capacitor should have a maximum reverse voltage of at least 10 volts. So I'm going to make it 10 volts. Otherwise, it's going to show me an error and it's not going to let us continue this simulation. So make sure you check these things. So I'm going to do an apply. Okay. Right. And I'm going to start the simulation. Right now, I did a right click and view scope. So what you see down is the input signal. You can expand this scope. You see a boundary line here, blue. Just click on it and move it up. If you want to zoom in to this waveform along the time axis, again, just keep your cursor or your mouse inside the scope. Use the scroll to zoom in. So scroll up and you will zoom in. And you want to zoom out, so scroll down. Right? So right now this is showing me the square wave. You see the label here. This is square wave generator. So this is the component it is showing me. Now I want to see the voltage across resistor and capacitor both. One important thing to note here is that normally in a digital storage oscilloscope that you would use in the lab, the DSO can display only voltage waveforms. It cannot show current waveforms by default. Okay, you've got to change certain things if you want to display a current signal there, but a DSO basically just measures voltage. So what we'll do in this experiment also is that we want to see only voltages. We don't want to see current right now, otherwise it will become a little confusing. So when you open this by default, you may be seeing two waveforms here. Okay, so please make sure that you do a right click, go to properties. These are the properties of this plot or the scope, and uncheck the show current box over here. Just have the show voltage box checked. Okay, if you check show current also, you notice that there's another waveform showing the current. So we don't want to see the current, just keep it as show voltage. Save this setting as default so that you don't have to do this every time. Apply and okay. Okay, so this is just the voltage. Now I want to see the voltage across this 1 kilo ohm resistor. So I'll do a right click here, click on view in scope, and here I've got the voltage across this across this resistor. Okay, I want to see the voltage across this capacitor. Click view in scope, and here I have the voltage waveform across this capacitor. Now, if I want to see them together, if I want to view them together, I can do a right click and do a combine. That means the left two waveforms will get combined and you see them in one single scope, just in different colors. Okay, you want to slow down the speed. So just from here, you can slow down the speed of the simulation, means the speed with which the waveform is traveling. Okay. What you see on the circuit here, the yellow dots, they show current, and they keep on changing the direction because of course the voltage is changing direction. So the direction of the current keeps on changing every cycle. That speed also can be controlled from here. That is just for demonstration purpose. It doesn't mean anything. You can keep any average thing. And this is not important from lab point of view, but this scope is important from a lab point of view. Now, whenever you are zooming in or zooming out, because you will be required to take readings, right? So if I just remove these scopes and want to just see the voltage across capacitor, so right click and view on scope. I'll slightly increase the simulation speed. Okay. Oftentimes, you may want to zoom into a waveform to get a better reading. So for example, I zoom in a little bit more. It is always good when you want to take a reading, click on run or stop. Okay. And when you see the cursor moving, you can get a value of time. You see over here, you see the value of voltage as well as time, right? On top. So these are your cursor readings. So suppose you want to take a reading at this point, and then you want to take another reading at this point on the curve. And suppose you're trying to find the time constant. That means you need a couple of points. You need initial voltage, final voltage, and some intermediate voltage to fit into that exponential discharge curve and find the time constant. So in such cases, whenever you are zooming in or zooming out of waveforms, please click on reset. Okay, because oftentimes what will happen when you simply zoom in or zoom out, the plot may not automatically update itself, and you may not find a significant change in time. So whenever you are zooming in or zooming out, make sure that you always click reset. So it starts from the beginning at that time scale. And then when you want to take readings, just click stop. It will stop the waveform. You want to continue, then you click this again and it will continue. All right. So for your lab experiments, we want you to take snapshots of these waveforms and also of your circuits. Okay. Now, always remember to save your work. So click on File, click on Save As, and then click on this link. When you click on this link, it will show you an option to download this as a text file. Later, when you're writing your report and you want to regenerate these waveforms, that time you can simply go to File and Open File and just open the text file that you saved. So all the files actually get saved in text format. Okay. Please make sure that you do not copy waveforms and readings from other people. Every group, as I've said earlier, needs to submit just one report with the names of both the students. You may use a TeamViewer remote access. One of your members can use a TeamViewer remote access to work on this project, while the other member actually opens this on their laptop or PC and shares the screen. Okay, so two of you can work together on this. So make sure that the circuit, the values are all correct as mentioned in the manual. So the manual will be shared with you. You will be asked to read the manual carefully for some time. If there are any video lectures corresponding to that particular experiment, you would be asked to view those lectures before, those videos before coming to the lab. And if you have any questions, please feel free to ask the lab instructor or the TAs. There would be an option to ask for help inside your breakout room. And you may also go to the main call and ask your question to the instructor, to the lab instructor. The broad headings of the lab report are already shared. Details regarding the video is also already shared. A template that you could follow will be shared shortly. All right, so please play around for a few days with this Falstaff simulator so that you acquaint yourself with all these options, how to zoom in, zoom out, how to use cursor. Another thing was how to view XY plot. So you may have seen in the video that I've shared earlier how a DSO can be used to plot XY plots. That means if I have two signals with respect to time, how do I show graphically the relationship of one signal with respect to another? That means I completely get rid of the time axis, and for every time instant, I have one point in space corresponding to X value and Y value. X and Y being the two signals. That's what's the XY plot. So you also have an option to do that in this kind of a scenario. So let me give you another example. Let me take a blank circuit. Okay, and let us say I want to plot the XY plot of two sinusoids. Okay, so I'm going to take a two-terminal AC voltage. I'm going to take another two-terminal AC voltage. They are both having the same frequency. They are both having the same voltage, 5 volts. So they are both sinusoids. They are both identical signals, right? Let me just change the value to maybe 10 volts. The other one had a peak value of 5 volts. This I'm making as 10 volts. Okay, I'm going to insert some wires, and I'm interested in viewing the XY plot. Let one signal, one of these inputs be given to the X channel, say of the DSO, and the other signal be given to the Y channel, channel 2 of the DSO. And in that case, how the XY plot between channel 1 and channel 2 would look like. I want to see that in this scenario, right? So here I'm going to use a label, output label. I want to connect a scope probe or a voltmeter. Where do I want it? I want it here. All right. And I now want to view this on scope. Let me start the signal. This is the first signal. I am viewing this one. And I also want to view this one. Okay. So side by side, I have two signals. Let me combine these two together. Okay. So they have no phase difference, but just a change in the peak value. Now, from the first video lecture on familiarization, and where we talked about XY plot and Lissajous figure, you already know that the XY plot for such a case should be a straight line, right? There's no phase difference. XY plot should be a straight line. having a slope which would not be 1 in this case. If the two signals had absolutely identical peak values, the slope would have been 1. Here the slope would be something different, right? Either 2 or half, depending on which one you are considering in x-axis and which one you are considering on y-axis. Now, how to display that xy plot? Do a right click, go to properties, plot xy. Okay, and here you've got the xy plot. If you look carefully, that point is going up and down and up and down. So here it already shows you when you click on the axis. When I click on the plot, you can see that the first source is being considered as x and the second source is being considered as y. Means on the y-axis, you've got the 10 volt peak-to-peak signal, and on the x-axis, you've got the 5 volt peak-to-peak signal. Now, these two signals had the same frequency, but just different peaks. If there was a phase difference between the two, that means let me give this second waveform a phase shift of 90 degrees. Okay, that's how it would have been for a capacitor or an inductor, right? If these were not two voltages, but say current and voltage across a capacitor, in that case they would have a phase difference of 90 degrees, and in that case you know that the Lissajous figure would have been a ellipse. Let us see if that happens. Yes, right? So we have a Lissajous figure which is an ellipse. Lissajous figures are also very useful when trying to detect which kind of an element is there in the circuit. Also useful for identifying what is the ratio of the frequencies between the two signals which are being plotted across x and y axis. So we'll share some content with you so that you can play around this a little better. But please feel free to experiment and form XY plot as well as voltage current plots for capacitors and resistors, and see the shape you would get if you were using a capacitor, means voltage current plot for a capacitor and voltage current plot for an inductor, and find out what would be the difference between the two. Take this as a homework. All right. So this was just to show how to make an XY plot. Within a few days of you practicing here, you'll be fairly comfortable with Volstad simulator, and we'll do many experiments like this on this platform. Thank you. Have a nice day.